Hello, everyone. Today I will present our research work on the faithfulness of vision transformer explanations, which has been accepted to CVPR 2024. Vision transformers (VITS) are gaining popularity in computer vision due to their effective use of self-attention mechanisms, which allow them to capture long-range dependencies. However, VITS are often considered black boxes because of their complex internal mechanisms, making it difficult to understand how decisions are made. This challenge has spurred the development of post-hoc explanation methods that produce visually convincing heat maps to visualize the importance of each pixel in making a prediction. For example, attention-based explanation extracts attention maps in multi-head self-attention modules and reshape the attention weights into image space to produce a heat map. These heat maps are intended to align with human intuition and help understand how the model arrives at its predictions. However, a crucial question remains: do these heat maps accurately represent the underlying reasoning of the VITS? This accuracy, termed faithfulness, is a significant concern as it ensures that the salience scores genuinely reflect the impact of specific pixels on the model's predictions. Without verified explanation ground truth, the evaluation of faithfulness poses a significant open challenge to the research community. To assess explanation faithfulness, common methods involve perturbing salient pixels and observing changes in model accuracy. Yet, traditional approaches, like cumulative perturbation, remove pixel groups sequentially and compute the decreases in model's accuracy, which may misrepresent the individual contributions of pixel groups. To advance the evaluation, we formally define the faithfulness leveraging a core assumption. The magnitude of salience scores signifies the impact. This statement introduces two essential properties for reliable explanations. First, property A states that pixels with higher salience scores should have a greater influence on the model's predictions. Second, property B asserts that a substantial difference in salience scores between two pixel groups should result in a noticeable difference in their impact on the model's predictions. Considering these properties, for a thorough faithfulness evaluation, it is necessary to explicitly compare the influences of input pixels with different magnitudes of salience, and to quantify the differences in salience scores to reflect the expected disparities in their impacts. In this work, we introduce Salience-guided Faithfulness Coefficient, SaCo, a novel evaluation metric that perturbs pixel subsets individually to directly compare their influences, as illustrated below. Specifically, given a salience map mx, y, produced by the evaluated explanation, we reorder the pixels based on their salience scores and partition them into k equally sized pixel groups, g_1, g_2, g_k. Regarding each group as a basic unit, we define its salience as the sum of salience scores over all pixels in that group. Then, SaCo perturbs pixel groups individually and measures the alterations in the model's prediction. SaCo conducts exhaustive comparisons among pixel groups. The fundamental principle underpinning SaCo is that a group with higher salience should exert more effects compared to a group with significantly lower salience, which can be reflected by the inequality here. This salience-aware violation test will go through all possible pairs of pixel groups and aggregates the differences in salience scores into a faithfulness coefficient. Fa higher F indicates greater faithfulness of the explanation. To validate SaCo, we conducted experiments on 3 datasets across 3 vision transformer models. We include 10 representative post-hoc explanation methods and compare our SaCo with 4 widely used metrics. We first test the interrelationships among evaluation metrics. Our analysis showed low correlations between SaCo and other existing metrics, indicating that SaCo evaluates a complementary aspect compared to traditional metrics. This demonstrates the significance and necessity of SaCo for providing a more nuanced evaluation of faithfulness. Recognizing the potential shortages of current metrics in assessing faithfulness, we conduct a critical examination to further demonstrate their limitations. we test the performance of random attribution as an explanation method, where salience scores are randomly assigned to pixels based on uniform distribution. An ideal faithfulness metric should return a distinct score on random attribution, setting a baseline to indicate a complete absence of faithfulness. We present a case study to compare the behavior of SaCo and AOPC, as indicated by their evaluation scores. SaCo effectively distinguished between meaningful explanations and random attribution, highlighting its ability to set a robust benchmark for faithfulness. We also extend this examination to large-scale experiments. As observed, SaCo consistently scores random attribution near zero, while most explanation methods obtain positive scores. This consistency underscores SaCo's reliability. By contrast, using other metrics, random attribution appears to have comparable performance, even surpassing some state-of-the-art methods. Additionally, our experiments reveal that all explanation methods perform moderately in SaCo scores, while those utilizing attention information generally perform better. We now delve into the designs of attention-based explanation methods that may augment their faithfulness through an ablation study. The result shows that the incorporation of gradient information and multi-layer aggregation brings significant improvements in faithfulness, suggesting that refining these two design factors may offer a promising path for advancing vision transformer explanations. Thank you for watching this video. If you are interested in more details, please scan the QR code to find our paper.